Congratulations on completing lesson 3.2. Jesse here again just to summarize what we've learned in this lesson, which has been all about the colors in the aurora. In the previous lesson, we looked at the mechanics behind the solar wind and how it interacts with Earth's magnetic field, connects up to Earth's magnetic field where the solar wind is funneled down those magnetic field lines to Earth's north and south magnetic poles, Earth's north and south polar atmosphere, particularly when we have this pinching effect in the magnetotail. As those field lines get pinched closer and closer towards the equator, they again reconnect. Those X points open up, the cracks in the Earth's magnetic field open up. The solar wind comes pouring down into Earth's atmosphere. In fact, it comes pouring down into the top of Earth's atmosphere. This is called the ionosphere. This is because the stuff floating around up here is ionized by solar wind, by ultraviolet light from the sun, and that kind of thing. For example, the oxygen that we breathe down on the ground is molecular oxygen. It's O2, and by that I mean there are two oxygen atoms sharing electrons in a bond called a covalent bond. But in the ionosphere, in the upper atmosphere, those atoms are broken apart. Sorry, those molecules are broken apart into atoms, into atomic oxygen. Atomic oxygen consists of 8 protons and 8 neutrons in the atomic nucleus, which is the green circle in this picture, and 8 electrons in orbit. And these electrons orbit in very specific areas called shells, or energy levels. As you can see here, there are 2 electrons in the first shell, and 1, 2, 3, 4, 5, 6 electrons in the outer shell, totaling 8 electrons. When an atom receives energy, the electrons can jump up into a higher energy state, or a wider shell with a wider radius, if you like. And when an atom loses energy, the electrons jump back down to the original shell. And when they lose energy, they have to do something with it. They emit a photon. A photon is a particle of light. Atoms losing energy glow. So, when a piece of solar wind comes in, a particle, charged particle from the sun, comes into the atmosphere, it bombards an atom of oxygen in the atmosphere. The electron jumps up to a higher energy state, and that state is an uncomfortable state for electron. It's unstable. The atom will soon decay again by ejecting a photon, as we've seen. And when an oxygen atom does this, up to about 150 kilometers, it takes about a second for it to decay. So it's unstable, it takes about a second for this process to happen. And when this happens, it happens at a very specific wavelength, a very specific color of light is emitted. The wavelength in this case, for atomic oxygen up to 150 kilometers, is 557.7 nanometers, or green, basically. The most common color in the aurora by far is green. That's atomic oxygen up to 150 kilometers, receiving energy from the solar wind, and then decaying back down again by ejecting photons in that wavelength, that part of the visible spectrum. But we also see a lot of other colour in the aurora. For example, quite often we'll see red. Red occurs higher in the atmosphere, and so if you're further south, like Kielder Observatory in the UK, you have good access to that part of the aurora display. Because it's so far away, you can see the full display from bottom to top, the green oxygen at lower altitudes up to 150 kilometers, and the red oxygen at higher altitudes above 150 kilometers. Now, the reason that oxygen could also glow in red is to do with the time it takes for an oxygen atom to decay. Now, in the lower atmosphere, it's denser. You've got a lot of oxygen atoms excited, floating around, and bumping into each other. And when they bump into each other, that doesn't allow for the ejection of a photon. But it takes under a second for the atom to decay, so the chances of a collision in under a second are actually quite low. So that allows for the emission of these green photons. But up above 150 kilometers, it's a near vacuum. There's not a lot of oxygen floating around up there. Now, when oxygen is energized and it returns to the ground state, the lowest possible energy state, it will emit red light. And it takes 110 seconds approximately for the atom to decay to ground state. Lower down in the atmosphere, in 110 seconds, there's going to be a collision. There's not enough time allowed for this decay to happen. It's only when the atmosphere gets thinner, high up in the upper atmosphere, that we can allow for the 110-second decay time to elapse. So that's the reason we see red aurora higher up. And red aurora often appears quite diffuse. At the very top of the display there, you can see that it just appears as a near solid wall of pinky red. And that's because in 110 seconds, the atmosphere is moving around, and so the aurora appears to blur, and we get that nice washed out red effect. So that accounts for the green and the red. Oxygen at different altitudes, decaying after it's been energized by the solar wind and ejecting photons. But like I say, we also see different colors. Lilac and purple are very, very beautiful colors in the aurora. And nitrogen is responsible for this. High energy solar wind penetrates lower than usual, lower down into the bottom of the ionosphere, and energizes N2 molecules, nitrogen, 2 nitrogen atoms in a bond. It takes quite a lot of energy to shake this atom up. Nitrogen is notoriously stable, but when you've got this high energy solar wind, it can do just that. And when it does, we see what's called a nitrogen fringe. At the bottom of your white-green curtains, you will see little bits of lilac and purple. They're absolutely stunning, and this is telltale signs of a very, very strong aurora display. And when this happens, I've seen it happen. I was there taking this picture several years ago. The pillars were appearing to abacus into each other. They were knocking backwards and forwards. It was absolutely incredible. And that nitrogen fringe was very, very prominent. You can just see it there coming in through the trees. We also have blue aurora. This picture, you get a little taste of blue aurora. Blue aurora is one of the rarest forms of aurora, and it's also referred to as sunlit aurora. And it's the product of sunlight passing through ionized nitrogen, which has been pulled up to the top of the atmosphere by electric fields in the aurora. Now, at the beginning of the aurora season in September in the Northern Hemisphere, and at the end of the aurora season in March, April in the Northern Hemisphere, the sun sets, but it doesn't set as low as it does in the winter. And so sunlight is still passing through the top of the atmosphere. Even though it's quite dark on the ground, there's still sunlight passing through the top of the atmosphere. And that's what's producing that blue colour as the ionized nitrogen, as the sunlight passing through it. So there's a bit of a recap on the different colours in the aurora and how they occur. And in the next lesson, we're going to start getting our teeth into how you can forecast the aurora yourselves, so that hopefully you can go out in the near future. That's all from me for now. I'll see you at the end of lesson 4. Goodbye.